Hello everyone, welcome. How we doing? Hey Chris, thank you so much for the sub, appreciate it. How you been? Welcome back, welcome back. Hi, thank you for the sub. How you been? So yeah, welcome back everybody. It's been about a month since I've last done this. Oh, glorious, thank you. Appreciate it guys. Excellent. Welcome back. So last time that we streamed, we left a little gift for myself. And it's oh wow, campaign as well. Thank you so much. He hath arise, my lord and Coda. Welcome, welcome back, sir. Thank you for the subs, guys. Appreciate it. Welcome, welcome. I've missed you all. Yeah, it's been a while. Like I was programming today at work, and I was thinking of my days. Just trying to understand some complex stuff at work. My brain was just getting fried today. So I left myself a nice gift, and it's another complex thing to sort of like get myself back into. But I've just been looking over it a bit before stream. I think I've got this. So I might spend the first like 5 minutes just recapping where we are, so it's easy for everyone to understand and or easier to follow along, I guess. But yeah, so we left ourselves right in the middle of this complex shader rework joys. um, but yeah, I think what I want to say is that while on holiday, I've not really done obviously any work on this project, but I did I took my laptop with me, and I did do like a design document. So if you check on the repo, there is a game design, and the reason why I've done a game design is because I've been doing some of this sort of like shader work, and some of the graphics is well, the graphics be a hell lot easier if we know what kind of game we're making. So I've gone and essentially outlined a game that we're hopefully gonna make, or at least some version of that one. So I'm just gonna keep working on that off stream, and then as it gets to a refined state where I'm happy with it, I'll talk a little bit more about it on stream. But yeah, that's going there in the background. So this means that when we have like when we do some features, we should be able to refer to that game design doc and understand what sort of requirements we have for the rendering, basically, rather than just anything. It's much better to have some requirements, some more specific requirements. So I think something that we want to do in this game, for instance, is I think our camera, when Milton wants to load, right, needs to do a bit of wine. Oh no, some .NET thing. So essentially, our camera is going to always kind of be pointing down to the floor, and that's something we can leverage when we render. There's a few things. So we'll have like, yeah. So I think we're going to have like, here's the eye. We might have a camera that sort of points down like this. Right, something like that. I don't know, maybe a little bit more like that. I don't know, or maybe not like that. I don't know. Ooh. Anywho, so this means we might not have to render stuff that's like super far away. Maybe the other one was better. But yeah, the camera might move though, but it would just be kind of restricted. So yeah, it should just be a lot easier to work with that way. So right, let's recap into what we was actually doing before the stream. So I was working on like a volume constructor, and so our volumes are basically this is wrong again. I wanted to go up to 1024 again, but I couldn't do that. The number is just too big. 1024 cubes is not, yeah, it's too big, man. So we're going back to the 256 cubed, and because I wrote that, the game design doc, I realized, you know what, 256 cubed ought to be good enough. So that's cool. So there's every time we say the word volume, what that means is a 256 cubed space that can be filled with, can be partly filled or fully filled with spheres. And so essentially the way we populate this area is, rather than storing 256 cubed space of spheres out to the disk, because that would be, I think it's like, is that 16 meg? Yeah, 16 megabytes per volume. Now if we have a whole ton of, if we have like 1,000 of these, right? That will put you up to 16 gig. Wait, is it gig? Yeah, that's 16 gig, right? So that's kind of a lot if you have that many volumes. So there's a method to sort of compress that. And the compression method we're using is essentially storing the history it took to build this volume. So inside the game, there's going to be like a way to sort of make these volumes. And I'm not sure if I'm going to expose this to the user, but I might. But it's definitely going to be there for people who are making the game. And the idea is you can essentially you have like a brush, and you can sort of put like spheres down or boxes, and then those will be the place of that the area that this intersects with the volume. That's where the spheres will go, basically, and you can essentially place down and rub out with these sort of things. So you can have you can put one edit down, for instance, and that will fill this area with spheres, and then you can have another sphere which comes in and cuts that out, basically, and create like a moon shape. And it's all filled with spheres. So we're just building that the set of shaders which takes those list arrays of edits, and then it will fill them with spheres in GPU memory. So the first one, so also as well, something to keep note is there's different LODs, right? So there's essentially like a full MIP chain in a sense, but in 3D for this volume. So there's one that's half resolution, half of that, and so on until you get to, I think it's 4x4x4, because that's the smallest size. So essentially it's a tree of clusters, and a cluster is 4x4x4 of spheres. So every 4x4x4, I guess this is it, there's a cluster. And a cluster, I think the way we decided to do the clusters were, yeah, I need to double check this. I forgot. I think yeah. So there's a 2x2x2 of children within a cluster, and each cluster has a 4x4x4 of spheres. And the cluster above, the cluster that sort of wraps these, that has these 2x2x2 of clusters as children, will essentially have larger spheres that represent a 2x2x2 set of spheres. So there's okay. You get the point, right? Here's its 4x4, and then by 4 along the Z. Yeah, so that'll just be the lower level of detail there. So we've got a couple of shaders which we've already done. This one constructs all of the leaf spheres, so it just goes over all the edits and paints down all the spheres, but we're not finished after we've painted down in the area. And the reason is because we need to fill in all these lower level of details. So for instance, when you paint down these guys, you need to fill in the lower level of details which cover which are in the parent cluster. So there's a tree of clusters, and the children are a high level of detail. Yeah, than the parent. So the parent are a lower level of detail. So then the parent of this one will cover all of those guys like that, right? So effectively, I've got the step here, which is generating those lower levels of detail. And this is what I got left halfway through. Oh, so this shader essentially has a queue. And I remember checking this last stream and it was all okay. So I'm just not going to bother frying my brain trying to make sure it's all right. But basically what this code does is it's just a queue of stuff it needs to process. And there's a whole bunch of, essentially, there's, every time a cluster needs to be processed, it gets pushed on this queue. We load it, we try and take it. If we can take it, we take it and we break out this loop. And yeah, so the way we dispatch this compute shader is we just basically launch as many as there are compute units times by some extra amount. And we just let those compute units just be super busy until all of the work has been drained from the process queue. So these ones to refine, I think. Yeah. Wait, what's this one? Yeah, when we construct our leaf nodes, when they find a leaf node, those get added to the refine process queue. So in this shader, we start off at the leaf nodes, and then we'll go up the parents, and we just push the parents back on the queue. So this is how we get around the recursion problem in GPUs, where you don't have recursion. Just push it back on the queue. So we've got our cluster, and now I need to edit the code below to it was designed for a 2x2x2 spheres. 2x2x2 set of spheres for a cluster, but now we've upgraded to a 4x4x4. So there's 64 spheres in a cluster, which is just far better to work with. 2x2x2 is too small. Hey, Ghost Goblin. Am I secretly making a new Doom engine? No, not at all. I'm not making a first-person shooter. Yeah, just some sort of like alternative rendering engine. So it's just gonna be a bunch of spheres and probably ellipsoids. And it's gonna be a bit of fun. There's gonna be like a different custom editor and stuff like this. So there could be some really funky stuff made in it. So how am I going to convert this to forward? You know, I'm going to leave this here and I'm just going to move the stuff up. That makes sense. So instead of voxels using spheres, exactly. And the beautiful thing is as well, is they're aligned to a grid in local space, right? But when you transform them into view space or whatever, they could be, you can have your little guy here and he could be boned, and then, you know, you can skin he's made out of spheres, right? And you can skin the spheres so they move around and all this. And yes, if you move them too much, you will see holes. But there's spheres going all the way through. There's not spheres just on the surface; they're in the middle as well. And yes, if you keep going too far, you will see holes all the way through. But that's part of it. But yeah, so there should be like bigger spheres in the middle, smaller spheres towards the edge, if you will. So they're not aligned to a grid when they're in the world. They're all moved around, which is pretty cool. So they should be able to be ellipsoids as well, because they should be able to be stretched. So it'd be easy to animate. I'm doing a voxel engine, but honestly, I just decided to avoid the animation problem altogether. Yeah. Voxels, you can't really... You can animate them in a few ways. I think what typically people do if they want to animate voxels is they'll just make them a mesh. And then they'll just sort of do the traditional skinning. Where they bend... Yeah, they make it a mesh, but they would add more vertices when they want the voxels to sort of bend, right? Which is fine. But yeah, this is a ray traced renderer as well, because I also want to have transparency, like proper transparency working. But yeah, we'll see how that goes too. Is your voxel renderer ray traced, or is it a traditional triangle rasterization? Right, it's this LDS thing. Have we still got this thing dotted about? Yes. Okay, spheres and cluster, that's changed, so that's no longer a thing. Okay, I see. This thing needs to probably change. So what we've got is we've got a node, a leaf node, which is like filled with spheres. And right, you're saying if it has a child. Okay, I get this now. So the first time when it gets the leaf node, it's not even going to try and create a lower LOD sphere. Excellent. It'll do that when it pushes it. Yeah. Right, okay, I got this. So 4x4x4, each thread gets a sphere within the cluster. Excellent. So, right. Let's try this out. So one cluster per, yeah. So this used to be 4 clusters per thread group, but now it's just one, right? And then there's all your spheres. There's a 64 thing, cluster spheres count. Boom. Constants all the way. Right. So that's your LDS memory. I think it's good to have LDS, we'll see. Right, so we set up LDS. Let's just delete this, let's just move it around. Right, I think we deleted the spheres array. Oh no, spheres exist. Oh, wait. I just realized the volume cluster node, that the spheres are just a bit set now. And there's 2 of them as well. There's an exclusive LOD spheres and a spheres, right. Cool. I did a ray tracer once, but this one is doing rasterization. I might add some path tracing post-processing after rasterization. Cool. Yeah, you know, if you've seen like if you have seen the ray tracing on Minecraft, um, like you can just tell like when if a game literally just has good lighting, um, you know, it it doesn't really matter much what the graphics actually are. Like, yeah, especially when it's the further away shots, because the kind of voxels are kind of smaller. But in a lot of the cases, there's just too much to process for my eyes to. But yeah, you get the gist with some of these shots. Now, the graphics don't have to be spectacular, even if they're just bricks, as long as the lighting is great. Rasterization is good since I have an AMD GPU. Yeah, that's alright, campaign. I'm still working on AMD. We're doing a compute based, no ray tracing API. Yeah, you can see he's using compute shaders as well. That's what we're doing. The ray tracing API in Vulkan is bonkers. Like it's just insanely complicated. Like I understand it, but it's just insane. And also, it's kind of like a step back. Like the way you see Vulkan is like going more and more towards like, you know, the lower level side of things. But then you get to like the ray tracing API. It's definitely a step back. I'm sure it's OpenGL there and Vulkan. Yeah, it's fair play. You just you know, if you don't want to do any serious engine development, OpenGL's alright. Unfortunately, Vulkan is just insanely complicated. Yeah. There's some nice parts about the API, and there's just a lot of like complication in it. Also, there's some really great things that you can do with Vulkan when you've done all the complicated stuff, or avoided doing a lot of things. OpenGL 4.6 has a ton of features. Teardown was made. Yeah. I don't think Teardown was made in like 4.6. I think from what I understood when I listened to a podcast, is he just used like a lot of like the old OpenGL features. I don't think he even bothered with 4 point whatever. Like for instance, a lot of his stuff was just packed into textures. But yeah, you don't need the latest and greatest stuff. That is true. But yeah, because we're using Vulkan, we do get to use like the bindless resources, which is really neat. Yeah. Yeah, so what have I got to do? What is the whole idea with using the LDSs? So the whole point is to create these spheres in there. So you might just need a bit set in there. 11, what is going on? No, not cluster tree LDS, what are you talking about? Ooh. That's copy paste error. Love me some copy paste errors. that cluster index needs to be in there as well. All right, all right, all right. So yeah, this one. So we're basically storing our spheres in LDS memory because we might not need them. Cluster tree LDS. Oh my days, that's a copy paste bug. Hang on a minute. Yeah, I don't know why there's these copy paste bugs. Yeah, I might have put those in there before I left, rather than when I last ran it, and couldn't. Yeah, I don't know. Doesn't seem right to me. But anywho, um, right. So cluster index that shouldn't exist anymore as well. Into these LDSs. Right. So here we go. So if we're the first thread within the cluster, we get the number of spheres, and then if so, we then allocate the spheres array, which we don't have anymore. Right, it just goes directly inside the cluster. Yeah, so I think it's better if we have LDS anyway, rather than all trying to write to the same memory location in global memory. I think it's better that way regardless. Maybe. No, maybe it doesn't matter. Optimization. Yeah, okay, so let's get rid of these boys. Okay, I got this. So, this setup LDS doesn't need to exist anymore. I think this doesn't need, yeah, it doesn't even exist anymore, right? Good. Cool. Okay, so this line here, remove the... Am I planning on to release this engine? Yeah, so right now, the code is up on GitLab. So for people who subscribe via Twitch or support via Ko-Fi, which is the preferred method for me because it supports me more, basically. It's the same price. Then you get access to the code, and it runs on Windows and Linux. Yeah, I think the Windows one is currently broken while we're doing this little rewrite or whatever, but I think it's Ko-Fi and then... Oh, wait, this was it. Code. That's the link. Yes, you have to link up to the Discord and then it gives you the link. But yeah, so after this, but I don't know. We are planning to actually make it into a game though. And the source code will probably ship with the game. Because I'm more interested in people potentially learning from the code base or whatever, right? Because it's a hobby project, so something will be sold and the source code will be sold with it. But yeah. So node children bit set. So we used to have like the children stored like a bit set on the... Yeah, we didn't have that anymore. Yeah, we're only using 8 bits. So let's delete that. Is child in bounds? What does that mean? Right, this was the bounds check. Just in case we index out of bounds and it destroys the GPU, crashes and all that stuff. So the way we need to index the child. Right, so that would have got the child node. Right, okay. So as we were saying, right, got ourselves a cluster, which is a 4 by 4 by 4. So there's another 4 going down the Z. So when you want to make this sphere here, right, this one right here, you're getting like, what's the way of saying it? Say if you're trying to make this sphere here, for this cluster, it's got a parent node, which kind of takes up all of this space here. It has a 2 by 2 by 2 off into the distance as well of siblings. This cluster node has, right? So there's this sphere which covers a 2 by 2 by 2 of spheres, and that belongs to this cluster here. There's another one there, another one there, another one there. Sorry, it belongs to the parent cluster. And there's another one here, another one there. Right, because that makes a 4 by 4, and then by 4 off in the Z. So when I'm in the parent cluster and I've got a thread for I've got, each thread is on a sphere. The thread, when it's building this sphere here, it needs to go into the children, the correct child node, look at the 2 by 2 by 2, and check if all of them are set, I think. And if they're all set, then this sphere can be placed down. And that's the logic we're writing here. So you need to get the correct child index as well. So I've already done this here, right? 0 to 7 inclusively. Yeah, so pass me has already done the maths. So thank pass me for that. So I've already got a cluster child index. Yeah, that's legit. So within the cluster, you've got your children cluster node start index, yes. Plus cluster child index. So all of the when a node has children, they're all contiguous in memory, and we'll just add to that, and that will fish out. Are we still doing it this way? I don't know if we're doing it this way still. No, I think we're just accessing the node directly of this. Yeah, so we probably want a bit of a safety check, I guess. Yeah, so we do set those up. Okay. So we want to say this is not equal to U32 max. Yeah. So if and cluster child index if that bit is set, something like that. So that child inbound stuff can now just go. Yes, less code. Okay, so now we fetch out the child node. Again, less code. Awesome. So this is where it creates that lower level of detail sphere. So we need to make sure that we look into the so every volume, it has 64 as a 64-bit set, but we don't have 64-bit integers on GPU, so we just do two 32-bit integers. So I forgot the way they're stored, but at worst it's just two samples, right? So we need to get a 2 by 2 by 2 set up, shift it into place, do the couple of samples, and then just check if they're all set. I think it's something like that. Then if they're all set, we can yeah, use that to you think you're gonna say if they're fully on? Downsample occupation map. What do we use this again? Right, so that checks if the thing was for. Yes. Right, so we might call like a pass bit set. I've done this above basically. Yeah, so I've done this similar sort of logic here. Just got to figure out how I need to set these up. Wait, where's the magical shifting thing? Ah, it's here. Yeah, no, I need some of this, isn't it? So we'll have Boolean. So we'll end up providing that this sort of child node dot spheres bit set, I think it's called. Yeah. See, and the pass bit set is equal to the same. Same thing there. Cool. So I just got to set this code up right. So how are we gonna make sure those bits? I just need to figure out what the layout is again of that bit set. So where is it? Spheres bit set. What do we do? Got to figure out how we index into there basically. Oh no, what is? Right. Oh, sphere bit set. Quite spheres. Oh, okay. Interesting. Wave active has sphere cluster index. Okay. Oh, it's this one. Right, so Z starts at 16. Yeah, so it's X, Y, Z order. Okay, so how do I get my offset into here? 2 by 2 by 2s. I need to figure out if I set a 2 by 2 by 2, and then I'll just shift it about, basically. Shouldn't be too hard actually. Where's that pass? Here we go, this is what we did. So this one just needs to be set up to mean basically 2 by 2, 2 by 2 by 2 is set. What was the other one? The middle 2 by 2 by 2, the middle XY bits. Yeah. Okay, I know the order now. Right. So if it's the first, so it's a 4 by 4 by 4, right? So the first row goes there, second row goes there, and so on. So it's 2 by 2 by 2, so that's 3, right? And then it'll be another 3. No. Hexadecimal, that's why it was looking weird. Yeah, so each like hexadecimal digit will be a row within a slice, right? Within a 4 by 4 slice. So you do 3 3. Yeah. It's the other way around, isn't it? I forgot now. Yeah, it's to be like I think that's right. So you got the first row, the second row, the third row, the fourth row, and now we go to the next slice, right? Because it's the 4 by 4 is obviously 16, and that's a slice. So 4 by 4, there's a slice, and behind that's another slice, and there's 4 slices. So it's basically 0 0 3 3 0 0 3 3, and then we do that again because it needs to be a no. The last one is 0 0, something like that, I think. So now we need to shift it into the right place. So I think actually we might need to do something like this. So what we're saying is well, we first need to work out probably the offset along each dimension that we need to sample from. So if you are so we've already got our dispatch index, isn't it? Local index. I think we can use this. And we literally just might have to divide it by 2 or something. And that might be it. Or remainder it or something like that. So we need to work out like what is that child I guess coordinate. I don't know what we're gonna put it. Spheres, something like that. So if you'd have another cluster over here that you can go into, or another one over here, and effectively if you've got, if your thread is trying to make this sphere here, this sphere here, or this sphere here, or this sphere here, then this would all be the same index, right, within the child. Same for that one. And then on a different one. Wait, I did these way too small, but you get the idea. This one here. This one here. So these guys will all be the same index. So how do we go ahead and do that? So it's just remainder in it. So then you say like mod what do you mod it by? Mod 2. So you only want it to be like 0. You only want it to be 0, 1, then I think you actually want to multiply it by by 2 as well. So I won't really call it. So when you're referring to the children here, you've got your cursor that starts up here, for instance, or wherever it starts, I don't know, wherever the origin is. And you've got this selector sort of like here, and you want to move it over there by 2, for instance, along the X. What's the best way to do that? Yeah, so if we say mod 2, that'll land us within here, then multiply it by 2. So that'll just be a... Let's be a 1. Yeah, because it's trying to work on this sphere index, so that'd be 1, 0, 0, then 1 along the X. Mod 2, that'd be fine, and then multiply by 2, so that'll make it an offset of 2, that's fine. I guess we'd call it that. Or I could call it offset. It's like a 3D offset, I don't know, coordinate maybe, it's fine. So when it comes to setting up the bit set then, so I guess it's going to either be 0 or 1. Sorry, 0 or 2. Now, either 0 or 2. Each component is either 0 or 2. So yeah, it's a similar sort of thing, I think. So the first one is that if it's shifted, I think this is just all zeros, not gonna lie. And that one's all zeros as well. So if the Z is 2, we'll just stick it. Yeah, that'll be the selection. Yep, that's right. Then we'll just do the shifting. So we shift. I guess this just makes it branchless, basically. So you're shifting probably just by x. So if you shift across by x, so your x is 2, and if your cursor's here, it will just move out, it will shift it over there. Should be alright. See, I wonder why this one needed to take ones. What was the problem with that? Either 1 or 2, that's why. Yeah. That's alright. So this doesn't need to do a take by 1. Then times by 4 because that'll do a whole row. But in our case, it might just be times by 2. Because you've already done a whole row. See, I wonder if the multiply is even worth doing, because you're just going to do it too many times. So you might as well just... Yeah, so say either 0 or 1. That'll be... And then we multiply that by 2. Alright, excellent. Right, so now basically we've made this bit set which allows us to check a 2 by 2 by 2 of spheres within the child node and tell if they're all set with a couple of operations, with, you know, populating these two registers or whatever based on a condition, which is like a select or a conditional move, 2 of those. And then we do a couple of multiply and shift operations, and then we'll do some comparison operations here, and that'll tell us if they're all set. So that's pretty cool. And then with this information, we can then be like, oh, because they're all set in the child cluster, right? That higher level of detail with the smaller spheres, and in the low level of detail, which has got the bigger spheres, we need to create one big sphere to represent those 2 by 2 by 2 of spheres. And that's what we'll do here, which is actually more simple than this. But I've got to figure that one out. So do I want to call it a pass bit set? Because I've done that down there as well, didn't I? Oh no, I didn't. Good. Right, so this is just going to be like, you know, basically saying like, has 2 by 2 by 2 spheres. If has 2 by 2 spheres. So here we're just going to say, check child node to see if it has the 2 by 2 by 2 spheres check the child node and see if it has the 2 by 2 by 2 high LOD spheres set that represent the higher LOD of... Okay, it's just a bit weird way of saying it. For our lower LOD sphere we want to create for this thread. Ta-da. So we do that there. Great. So now we create it. Now a cluster used to have like more information, like a material on all of this lot, but I kind of like moved that to a different tree of information for customization reasons and whatever. So I think a lot of this just goes. So I think we literally just say, hey, we index into the array, and then we get the sphere's bit set, and we need to index an OR into the right place. So here's me figuring it out. Oh, damn it. Right. That makes sense. So you kind of just want to index based on if that is greater than 0. Right. So if that's greater than 0, it'd be 1. If it's not greater than... Wait. 32 or something. Yeah, if it's greater than or equal to 32, then it'd be 1. And index the second bit set. And then we need to mod it to land our bit in there. So I think we've got that. Yeah. So this is 0 to 63 inclusively. Excellent. So that's the wait a minute. I'm indexing that. We want to then want to OR equal the one shift left of that. And voila. So that will create the lower LOD sphere, store it in that in the parent node. So a lot of this just now goes, which is great. Deleting code, yay. So now this one is saying like, hey, well, we've now removed the child. Sorry, we've now made the low LOD sphere. But is it possible to remove the child node? Wait a minute. Maybe this needs to go in a different place. But because it used to be a cluster and the children used to be the same size, like the number of children, number of spheres used to be the same size, but now it's different. But the basic idea is saying, we've looked at this child node, and if we no longer need this child node, because we've created a lower LOD sphere, and it's completely surrounded by other clusters, we might as well just delete this one. That's the basic idea, to save us some memory. So we can store more spheres on the GPU and just use the bigger spheres in the middle. This is how we do the bigger spheres in the when I was saying, hey, in the middle of a volume, you have a bigger sphere. On the edges, you have smaller ones. So this is what we do. We basically come over in this pass and clean it up. So this needs to be moved into a different place, I think. We probably want to tally, like, did that child cluster, yeah, we probably want to have a thread which goes over. Okay, we'll look into this. What was my tunes? Yeah, so I think we want to have probably just 8 of the threads going out of the 32. Yeah, so we use the occupation map to tell if it's surrounded by other clusters, basically. There's nothing special here. Yeah. So what we're going to do is we're going to be like, right, if your sphere index is less than all right. Move all this in a bit. Okay, so if your cluster sphere index, oh my days, messed that one up. If your cluster sphere index, which can be 0 to 63 inclusively, is less than 8, so what the first 8 threads going at it. So we'll just let these guys go ham, and each of these is going to get a child. Um, hmm. See, the way this one makes this child index is yeah. Forgot how it does it. Yeah, no, that's not good. That's right. So I guess we'll just use this sphere index instead to get the child. So we'll have to say so use cluster sphere instead of cluster child index as will be 0 to inclusively across the active threads. Whereas, you know, we'll have repeats. Yeah, something like that. Instead of the full range. There you go. So we're going to get the child node. And so we use that new child index thing here. And then we'll say, okay, if the child node so how can we get rid of it? I think there was a certain when I made my occupation buffer occupation map, I think I added there's a way of checking if it was oh no, that's the downsample, whoops. Here we go. Mostly full count. This is the one we want. Yeah, I kind of want one of these. So what's the idea with this? Well, we should be doing some atomic store here, I think. Cool. So this one wants to... what's up this mostly full thing? Yeah. So in a 2x2x2, I think if you miss one, maybe it's okay. Maybe we can do count bits here instead of make sure we have a complete. So if we did bit count plus bit count has 2x2x2, so instead we'll say count of 2x2 spheres, I don't know. So if that count is, let's say, you know, greater than or equal to 7, right? So you're given like an off by 1. So you can have, in a 2x2x2, you can have 1 missing, and then it'll still create the lower LOD sphere because it's probably good enough. Yeah, it should be fine. Yeah, there you go. So in this case, when we do this mostly full spheres, it's the same sort of principle. There's some missing. There can be some missing, and if there's enough missing, and if there's enough spheres there, then we can remove. We can remove the child so long as yeah, we can remove the child so long as it's surrounded by other clusters. That's the idea. All right, let's give that a go. So exclusive LOD spheres again, what does that one do? I always forget what this one means exactly. So when you're exclusively rendering, yeah, when you're at that LOD, use those spheres. That's right. When you're at the LOD, use those ones instead. So if you have a shape, if you want to get a specific shape from lower level of detail, you can. If the automatic one isn't good enough. So when it's creating the oh, we don't have that separate pass now to create the occupation map. That's pretty cool. It does it all in here. Excellent. Hmm. Right, so if it's the leaf node, okay, it makes sense. Okay, so for this one though, um, because we're not using the exclusive LOD spheres. So just to make it clear what the exclusive LOD spheres mean, like you got your cluster here, which is 2 by 2. Oh, sorry, it's 4 by 4 by 4 of spheres. You know, we only create a lower level of detail, which is a bigger sphere for it, so long as there's like 7 of them here. But say if if there's 7 out of the 8 or more, right? Here, we only create that sphere. But say if you've got 6 or whatever, and when you sort of zoom out, it just sort of feels like there's something missing. So you can the artist or whatever can explicitly paint over some spheres for that LOD and just make it so it just looks a little bit bulkier in places where it needs to, effectively. So I'm just a bit curious of when we do the automating of oh. Yeah. The automatic should only be for the spheres. It said these. Yeah. Yeah, when we create these, the LOD, it should only be for the spheres bit set, not the exclusive LOD spheres bit set. So the question still remains then for this one. When we're trying to see if we want to get rid of it. Yeah, I do think we need to OR all the bit sets together for the exclusive ones, because this is when you're trying to view it at that LOD. Yeah, that's correct. Okay, so if the count is greater than this, it means we can try and remove it. So we can shift all this back in. Okay. Right, so try to move the child if it has a leaf node. Sorry, if it is a leaf node and is fully surrounded by other clusters with the full set of spheres. Yeah. So how do we know? Because it deletes. Right, then later on it will clear the bit set here and put it back in. Right. Interesting. Hey there, Peter. Peter Riggs, welcome. Thank you. Thank you, sir. Yeah, I arrived back on Friday and I had 4 hours sleep over 48 hours. So yeah, had a good rest. But still very tired though. I've been sleeping well. Yeah, I've been having like 9, 10 hours. But as you can tell, I'm a bit tired right now. I've been waking up at 4:30 past 2 days. So hopefully, because I'm staying up later today, I should uh yeah, should hopefully be waking up at a sensible time. Not super early. But yeah, I missed the streams too. Yeah, it's been great getting back into it. I left myself right in a pickle where it's like, hey, you're halfway through some complicated work, but we've been managing to carry on just fine, I reckon. So yeah, I'm hoping to get this shader sketched out today actually. This refactor for this shader, and then we've just got a couple more. Or I just think it's just one tiny shader, another sort of biggish one, I think. And then I can see how the hell I'm going to get this thing back up and running again. Like what I'm missing, basically. Yeah, good old jet lag. Oh, it was crazy. I think you had like a 14-hour flight and then stopped in Dubai for like 3 hours. And then had another 8-hour flight. So, a full day worth of travel. Literally. Diabolical. Right, on that note, I might get myself another tea. Because I need a drink. But yeah, I'll be right back. Just gonna make myself a nice cuppa. Right, welcome back everybody. I got myself a nice cup of tea and a Freddo. Can't believe they still sell these things. So, yeah. Where are we at? Tries to remove a child of leaf node. Right. Yeah, I was just doing some funky stuff where we saw the edited version in the higher bits. But we don't need to do that anymore. Right, so child is a leaf node. Get the position, get the coordinate. Yeah, this code all stays the same. So that's great. So essentially there's a texture which we've made in a previous pass. So this is something that's already been done and tested. And it's got different MIP levels. And basically there's a bit set. It's a 3D bit set texture. And essentially each bit represents a cluster in the 256 cubes volume. I've got this somewhere, I know. Yeah. And effectively we do some tricks to make it so we can sort of like what's the best way to just quickly explain it? Right, so essentially like it's a 4x4x4 bit set, right? So it's a 64-bit integer. And I think this is the unique information, and this is repeated information from the neighboring bit sets. So this one comes from the bit set to the right along the x-axis. This one comes from one along to the right and down. This one comes from the down, right? So effectively we have a way of like within two samples, and it would just be one sample if we had a 64-bit integer. But within two samples from the texture, we can essentially say like, hey, we've got this cluster which is here. Check to see if all of the neighbors are surrounding me, and we can do that with two samples and then a bunch of and a couple of bitwise checks. So we just have to make sure that we land the cluster that we're sampling in the middle, so it's not like at the edge of the bit set, and then it just works fine. So that's what this magic does here, basically. It's pretty sweet. So, but this bit, yeah. So what we should do is do an atomic and remove it. So I want to get the cluster, get its children bit set, and let's just nuke it. And we should probably also clear all the other bits and bobs as well. That's what we're doing. Yeah, I want to do that. Yeah, child index. So we should probably clear these guys, right? like just clear all that. Right, there is the cluster nodes. Hmm. Right. So he already has no children. But we should definitely do is look at the sphere's bit set and then set that to 0 and do, you know, the full bit set. There's 2 parts to it, right? Same with the exclusive whatevers, right? Those should be cleared as well. That's already invalid. But we got no children. I think that's probably just fine. I had to do that. So this is like, you know, remove child from, you know, current node. Sort of, you know, clear, you know, like reset the child node's data, or clear, right, for sort of safety basically. All right, so there's still a few things I want to do after this now. So we want to make sure, so if all of the children have been deleted, then we don't need the allocation around anymore. So we should really be able to push that back on the stack basically, of because it's that's the way the allocator works. So what we should do is we should probably do one of those thread, because there's 2 ways that run out of sync. So we need to make sure we synchronize. On a control barrier, put on dispatch group. Oh, probably want to control barrier all. That reminds me, this is all right. Yeah, this wants a control barrier all. And then want to go, and then want to say, hey, with the first thread, then do an atomic load on this. And, you know, if it's all equal to 0, then what we can do is probably delete it all. Now, what was this code all doing here? Pack the final bit set in the higher bits. We don't need that anymore. That's just some, because the way we designed the previous version, which we refactored, or which we're in the middle of refactoring. This one was saying like, well, if you have spheres, then sort of allocate the spheres array and then like populate it and all that. But we just have bit sets now, and they're all, so this can just kind of all go as well. Now do the copy, and this allows us to go up to the parent, right? So we want to make sure we can sort of deallocate the memory. So where we do that is, just got to find it. Is it an atomic sub or something like that? Cluster tree leaf nodes count. That's not it, is it? Wait, what's that? No, that's old code. That's way old code. Ah, here's a version of it. Right. You want to put a slot back on. Man, I'm not sure how we did this. Oh, so they're bump allocated. Bump allocate, right, and it'll do a copy later on. Yeah, excellent. So what we've done is we've got an array which has the maximum allocation where all the tree nodes go, but we don't care about deallocating those because when we do, we basically copy the whole. We have a temporary space of memory where we're building the sort of tree in here, basically, and it's maximum allocated. There's a couple of these arrays. But what we end up doing is we copy it to more of a persistent place in memory, or the parts of it which persist and haven't been cleaned up and deleted. So that's the gist. Okay, so this means then this can go as well, less code. So now all we have to do is figure out, yeah, so if we have a parent, then we can go up to we don't have any parent indices? What is that about? I must have got a... Okay, let's see how we didn't get a parent in there. How do we set a parent and why? Why didn't we do that? Oh, because I thought it was only going to go from the top down, but actually wouldn't go bottom up in this right. So I didn't bother setting parent. Okay, doing a parent. Okay, that's fine. No worries, just put one in. So we could probably stuff it in here, but you know, wait, how many bits? So that's 1, 2, 3, 4, 5, 6, 7. Those can probably be crammed together, and that'd be 8 integers. Wait, no, it'd still be 7 if I had that one. Yeah, we can figure out later. So let's just be parent node index. So that thing needs to get initialized and all sorts. So here's the root. The root is going to be set to U32 max. This one is when we... Right, yeah, when we do the construct of the leaf nodes. So how do we get the parent then? This isn't even a real function. Atomic store U32. Yeah, so I need to set it to like cluster node index. I think that's what it's called. No, if the naming was consistent. Alright, it's just cluster index. So that'll store that in there. Excellent. Right, I think we're right. Okay, so that's now got all the parents set up for every child that you make. What else? Yeah, I need to fix these atomic stores. I'm gonna fix those anyway. So let's just do that. Boom. Right. So I need the parent index basically. So I say, hey, if this node has a parent, then we want to push it onto the we want to push it onto that queue. So there's a thing called like a refine process queue. Now I think we do some extra special bits and bobs. Yeah, we need to push on like a generation on here or something like that. Spin until all the potential children for this cluster have been processed. Yes. I need to figure that one out. So, insert index. Okay. So what you would have done is you'd have processed a whole cluster. Yes, I figured out a way how to stop a problem from happening. So I've got to figure out what that problem is again. So spin and wait until all the potential children for this cluster have been processed. But how do we avoid pushing the same node on? How do I? So there's going to be a 2 by 2 by 2 of potential children, and I need to know they all have a parent. They all have a parent. And the problem is they're gonna all want to add the parent in there. So we can use some bits. We can use some of the higher bits in this children bit set to say, hey, these ones have done refining. And the last one to sort of do it is the guy that pushes it on the. We did this before in the past. It's a thing we could possibly do. I'm just trying to remember. Oh yeah. If the child cluster sphere index less than so if it's the first thread for this cluster, we want it to reach into the parent. So be like BC volume cluster nodes node.parent node index child or children bit set or something like this. See, I could poke some, things in the higher bits there to say, oh, we've finished refining these guys. And it will just linger there. Oh no, it can be removed, actually. can be removed. I don't think there's another elegant way to do it because there's just different compute units at any time accessing sibling clusters. So it's not really going to be easy. So I think we'll just do like an atomic bit or E32. So for that we want to, I think we have like a child. Well, how do we know what child we are? It's a difference. Parent-child index, that is going to be, you've got like the, oh, it is, you get the start index where all the nodes sit. That's the smaller number. The bigger number is obviously the cluster node index, or is this called the cluster index? Yep. So that'll get you your offset. So you can then use that. So I think we'll just do a one shift left, that times 2. Wait, not times 2. There, I meant times 2 here. So shifted a little extra. So it returns the original value before you did it, right? So I guess you want to call it like the bit, I guess. And then you want to all that bit on there as well. And then this will be essentially the bit set. And what you want to say is if the bit set shifted right by 8 is equal to, oh no, the baby's up. Little man. Poor boy. Oh no, the little man's up. Alright. I'm just gonna take a little break. I'm gonna deal with the baby. Try and get him back to sleep. I'll be right back. Alright, welcome back folks. Just sorted out the little one. Alright, yes, what was that? Is this, we're just sort of checking to see if all of the children have finished and tried to set the parents. So we're in the bits that come after the first 8 bits, we're storing wherever or not they have finished, basically. And they're stored in the parents child bit set. And first 8 bits. Voila. So that is the case. Not a leaf node. But yeah, we'll sort out that comment in a bit. So that's basically all of that code now. Just a little less of it. Cool, so it's got to say continue though. Wait, why would they terminate? Always continue. Because it continues back around and gets the next. Ooh. Something's wrong here. And gets the next job from the queue basically. And I need to put in the iteration. Oh, what is all that? No, that's wrong. Right, something's up with these brackets. That's alright. That's alright. Okay. Right, where does this one end? Oh, there you go. Alright. Yeah, so it goes back around again. Okay, so I think let's get the comments around here to make it a little bit clearer. I've also got to, when we use this children bit set now, I've got to be careful. I think. Yeah, I've got to look around with that one. So, so essentially say like, you know, the sort of actual bit set. So, low 8 bits, is the bit set. 0x is, we'll probably want to call this like, is used is the children that have been refined. Okay, something like that. Yeah, I think we'll have them set then. So we are the final child to be refined. So add the parent node to the refine process queue. So it gets picked up by some other compute unit, it just does, yeah, it goes full ham. So we need to get that parent, that plops in there. Now we need to do something with this. We need to add like a generation. So these generations, right, we'll need to store that in LDS, I think. Interesting. Goes. Oh, come on. Right. So in LDS, what are we storing again? The generation. So effectively we have an issue. Another compute unit. Wait a minute. What's the issue again? Figure this one out. Yes, the issue is that when you pick a node up, could its children still be... Actually, maybe it's no longer a problem because of the thing we've just done. Yeah, they're all down at that point. They've all been refined at that point. Yeah, we didn't have to do this spin and wait thing anymore. Excellent. Right. That makes the code way better. So all this generation nonsense can just go. And that just simplifies the whole process. Oh yeah. Man, I love it. Okay, so what is this saying? Oh, this spin logic. There's got to be new. Alright. I gotta go and grab the other logic up above about this head and tail thing to see how different it was. Or is. Alright. Mario. Put it up there. It's out the way. So, head. Right, it's just that bit goes. It's all the same. Excellent. So effectively it's just taken from a queue in a multi-threaded way is all. Then takes the next job and then goes for ham. Okay. So we just got to be careful with these child bit sets, is that right? Or children bit sets? Yeah, we've got to be extra careful with those. It's not equals 0 anymore, and 0xff equals 0. Remove child from a current node. Yeah, that should be alright. And then this one will... Yep. Sweet. So I think that is this refine LOD stuff all sketched out again in the refactor. So what is left? So it goes up the tree, and it will create the lower level of detail spheres. So now the final shader is basically copying it to more of a persistent space in memory. And I need to think about the way I want to do this. I've got some time to do that. So we've got in this sort of temporary building space. Now I kind of forgot. So there's like an internal, isn't there? Yeah. So these are the sort of buffers we've got. So constructor cluster nodes, process, construct process queue, refine process queue, occupation map. Yes. So essentially we take this, like this is just some like massive buffer that's just the maximum size for a full volume while you're building it, and then we compact it into the sort of shared buffer. Like there's an even bigger buffer, which is where all the persistent volumes go after they've been constructed, and it's more compactified, right? So yeah, it's not too difficult. This one resets the volume. I'm not sure why. Right. So the volume root node is 0 is the first node. Okay. So what is probably a good idea is just to store them all, you know. Well, ideally, you want all of the LODs, or maybe not. Yeah, maybe it's better if they're next to each other. We'll see if we can do it. So all the LODs on the same. Oh right, all the siblings are already next to each other because the way the system works. Yeah, all siblings are already next to each other anyway. So it literally might not matter how they're allocated. But the root node will definitely be at 0. So when you do this sort of volume reset, you kind of need to know like, hey, what's the maximum number of use this to bump allocate and make persistent. So this is the old code that we had, right? Right. But we had a to-do for like actually allocating it. So the idea is that we kind of want to have the number of nodes stored somewhere. How are we going to do that? Can we get that number? So we mark it for deletion. I don't think it's too hard, right? We just count. We've definitely allocated. Wait, where's the globals buffer? So in the globals buffer, we've definitely got a tree nodes count. So with that, we bump it. Yeah, easy. So we literally just need to sub it, and then that's the one we subtract it, and then that's the one we need to use. Subtract 1. So here we sort of, you know, the total number of tree nodes. Now, That's actually not correct. You don't do it one at a time. You kind of want to do like all of the children. So you really only want to do this when. So I guess we do need the if statement. So if you're the first thread, you want to say, well, if the node, so atomic load, so if that is all equal to 0, so you want to say like this node no longer has any children. So sort of subtract the total number of tree nodes. There you go. So now that number is the one that we use. So in this volume reset, we need to allocate allocate it somehow, but we're saving that for a later date because right now we're just going to be testing a single volume. So we'll just plop that in there. It's not a midpoint cursor anymore. What are we talking about? It's I guess the tree node start index. Oh. Sure. So yeah, we'll use this to like find our allocation. So we set that to 0 so we can bump allocate. And voila. So now the make persistent code, the way this one's going to work is. So I guess we could start now. We could start the parent and traverse. So we could start the parent and just traverse down the tree. Just trying to think how we would do that. Or if that's the better way, the best way. Traverse down the tree, copy. Yeah, and stop traversing if you reach a child bit set with nothing. Yeah. So I think we'll basically do a very similar thing to the construct. So what do we call it? Yes, it's a process queue. So I guess we'll do another set of these guys, and we'll call this one the sort of make persistent process queue. We might not even need this. Yeah, to be honest, we probably just need to reuse the construct one. Because yeah, so we'll clear that up and put the root node on there as well. What puts the root node on the queue? That's a good question. Why actually puts the root node on the queue? Yeah, we didn't even put it on there. Oh, we did, right there. Right. Yeah, so put the root node on the queue. Construct process queue. So we need a process queue now and there, and in the make persistent shader. Fantastic. Right, so we should have reset the necessary state here and added the root node to the queue. So now what we need to do is grab that queue. There's a wait count as well, actually. Does that get reset? That generation needs to go. Does that get reset? All the right so this is the wait count, and when they're all waiting, it kind of needs to be reset so it will return. Because like we use that in the refine. You know what? We'll just add another one. So this one is the construct one, and then there'll be a refine one as well. Just makes it easier. Otherwise, I have to make another shader or something, and it'll just reset this data. Oh, this is the refine one. Whoops. Yes, there'll be a refine one as well. And I just got to make sure that we reset this in that volume reset, which is before the make persistent shader is called. So this yeah. Right. So in the tree constructs, which is the first shader which kicks it all off, this. No, it's not the tail one. What am I talking about? Search for the wrong damn thing. It's that one. The wait. Very nice. Now this one is the refine. Okay, so now all this lovely sort of so I think it's just the queuing stuff I want. So I don't know how many. I think we're just copying one node, one cluster, a thread. I think. Okay, so we're just going to do this, and we'll just rewrite the shader again. But we'll just obviously keep an eye on what's below us and copy that over where necessary. So this is just going to basically pop off that, take the root node off the the queue. So it takes the root node off the queue and then it'll store it in some LDS memory. Why is there a children bit set? Right, it's in the LDS. Right. Need some more LDS memory, I think. Hey there, Meatball One, how's it going? How you doing? Yeah, doing some insane stuff on the GPU. Just, horrible code. But yeah, should be alright. Should work. But yeah, just got back from a holiday. So I left myself right in a pickle before I started this. So just, halfway through a complicated refactor. And as then insert a month of holiday where there's no programming and then come back. My observation is that we do not have decent tooling for elegant GPU program GPU. Yeah, that's very true. They don't have pointers. It's bananas. Bananas. I think there's a little bit of LDS memory for this. That's how you spell it. There we go. Oh yeah. Final shader. And then we can figure out how to plug this thing all in. Well, it's already kind of been plugged in from the CPU side, but yeah, just make sure it's all right and kick off one at a time and debug it so it doesn't blow up the computer. Excuse me. Oh wait, it's still the rendering code that must change. Yeah. Right. So here is where you have access to that. You'll have access to that cluster. Right. So yeah, what are we doing again? Yes, you get each thread gets a cluster. Oh. So maybe we don't need to have LDS at all. Because I need to share it between the waves. Alright then. Get rid of that, and kabam. Cluster and boom. So yeah. Now you just got to figure out if you're going to make it persistent or not and copy it to the persistent place in memory. So the way we tell that is I think we just check to see if it has children. I mean, then you're going down the children, isn't it? Yeah. I think I can handwrite this. So you want to say like, hey, if the node children bit set and this. So if it has children, you need to bump allocate a destination node index. But yeah, I think there's actually two. Yeah, there's a source nodes. Right. So this is, you get this by bump allocating from the, I think there's a global, oh no, it's in your volume, isn't it? You bump allocate in the volume, these counts here. Address of this point. Boom. It's kind of relative from your start index though. Yeah, we need this one. Just sort of sit in there, you know. Oh yeah. So the node start index for all of for the whole cluster tree. So we add that to there, and that should really start with DST for destination. Okay, so now we should literally just be able to do a copy. So I'm going to say, hey, DST equal node. So we copy the node over into there. There might be some patching as well of the children or something. I forget. But yeah, we definitely need to like probably clear out all that sort of children bit set. We probably just want to like just keep those lower bit. Just keep the lower bits and not those higher bits because they're not really used. They're just used as a temporary place. Yeah, so, you know, those upper 8 bits are only while we're building the volume. Only while building the volume. So we can clear them out here. So what else is going to be an issue? Like, so this node. Well, no, you want to keep this node regardless, right? Yeah, you want to keep the node regardless, but if it has children, then you want to make sure that you allocate. That's not right. Hmm. So effectively, each node has it can have 8 children, and they sit contiguous in memory. So you need to have a way to sort of like copy all of those over, or set them all up basically. What does it mean that you do children bit set? Yeah, so we only need the first 8 bits. Yeah, so we only need the first 8 bits because we've actually used some of the higher bits to mean something else. This is just basically saying like, does it have any children? Um, yeah, that's what that means. So we'll be saying like, in here we're just making it so only those the bits that represent the actual bit set are set rather than those extra bits that we've been using while we build to sort of keep track to see if they've been the children have been refined or not, and therefore the parent can now be refined and simplified basically. Sticking another function in has children. Yeah, probably a good idea. Yeah, I have to do a macro though on GPU, but I see what you're saying. Yeah, definitely a good idea. Um, yeah, I'll probably do something like that in a cleanup pass when I know exactly what the code is. But yeah, definitely need to do something like that. Make it a bit clearer. Um, so I don't know what we would do because it's as if you need. So I need either both because you don't bump allocate it like this, right? Because they've all got to be sequential. They've all got to be. Uh, so we could give 8 threads. So we could process 4 clusters in a single wave. 8 threads for all the children, so you can do in a single instruction. You can do yeah, you can do the you can add them to the queue or something like this. Add all the children to the queue or something, or maybe a better way is actually make them persistent. Yeah. And someday we can discuss the question, what is a function exactly? Yeah. Well, yeah, macros are just, yeah, it's kind of functions, but, inlined in the. Man, the whole LOD concept is so damn significant, yet also very difficult. Yep. Yep. It's, also as well, the version I've done doesn't, like, it definitely has, yeah, it definitely has limitations, put it that way. But I'm okay with these limitations for this game. I have an idea for an improved version, but it's just too much more work. So I'm just sort of drawing the line on this one, and just basically getting moving on, because I spent too much time on this LOD stuff. I think I spent like more than 14 streams on it. So yeah, it's getting a bit long. 8 threads. Yeah. Well, yeah, these are not technically threads, they're just SIMD lanes. Yeah, GPUs are awesome. But the software stack is terrible. Mm-hmm. What's kind of interesting is um what is that Intel compiler? ICC? Is that what it is? Um yeah, I forgot what it is. But effectively, like, you can already kind of do like shader-like programming on a CPU in a way. Like, but except for it's like 8 lanes on Intel, but maybe they do 16 lanes. But effectively, just compiles out to SIMD instructions. They have a way of like, I'm not sure if it's the ICC compiler, it might be something else. But effectively, you can write like normal C looking code, but it actually sort of compiles it out to be somewhat like a GPU works, and it uses like SIMD basically, because you know in if you fully like if you were to fully use SIMD, you're effectively getting multiple threads that run in lockstep in a way, right? They operate on 8 floating point values in one instruction. Is each lane considered 32-bit like an int? Depends on the hardware. On GPUs, yeah, some GPUs only support 32-bit, but a lot of the modern ones support 64-bit. And sometimes the modern ones just literally use two 32-bit ones, and you just get less VGPRs or less SGPRs. That's what AMD typically does. Um, and yeah. Mm. Right, so after this shader, what have we got to... So it's just making it persistent. And then I think I've just got to make some edits where we did the rendering. Because we definitely like copied it. Yeah, I did the whole... We sort of copied the spheres basically. I wonder where we did it. Or delete all that code now. Yeah, so much just like unnecessary code in here now. It's in the tiled stuff, wasn't it? Yeah. Yeah, I think I did something here. Yeah, so I can just edit some of this code as well, and then maybe we can try and get it up and running again. That'd be interesting. Yeah, so maybe next stream we might start getting up and running. That'd be cool. So I think I'll put a pin in it here today though. So we'll finish off this make persistent next stream, which should be on Thursday at 7:30 p.m. GMT. Yeah, that's right, GMT. And hopefully get this thing all compiling, I reckon. That'd be awesome. Oh. Hey, Cranston, how's it going? As far as I know, generally a lane width is per instruction, I think. Yeah. Yes, yeah, that's true on Intel, yep. Yeah, that's right. Yeah, that sounds about right on the Intel stuff. But yeah, that's kind of how the GPUs work as well. Like you can store floating point and integers in the same sort of registers. And what's weird about the GPUs as well is the registers aren't. They're kind of in like some sort of L1 or L0 memory. They're like technically in this sort of like cache memory, and then they're loaded in, operated on, and stored back. Like from what I understand, at least. Because they just have so many registers, and they hide the latency by. Wait a minute, no, that's a different thing. Yeah. Anyway. Right. Let's find I suppose ready to see who's about. It's not doing any programming. Man, I'm so tired. But at least I've probably adjusted to the time zone now, I think, because I managed to stay up this late. So we'll see. Do we see any C's? Or any CPPs? Or anything else that's sensible? Right, this TCAP one, there we go. Right. Yeah, thank you for coming, everyone. I'll see you all on Thursday, if not Sunday. And I'm hoping soon that we can get some of this LOD cluster stuff up and running again. Pretty sweet. And yeah, do some more rendering stuff. That. I know, right, man. I'm so knackered. Thank you, Campaign. Appreciate it. So have a good night. And yeah,